Assalamualaikum and good day everyone. So I try to record as short as possible because my phone run out of memories. Okay, it may be unintendedly stopped. Okay, so now is 17 May. Okay, 17 May 2021. It is around 2:56 a.m. Okay, so we proceed with magnetic flux density. Okay, I just using these books in hope that someone that didn't have the Sadiko book, okay, actually have to benefit from this. Okay, so but we have, like in electrostatic, we have electric flux density, am I correct, which we shown as D. Okay, in magnetic flux we also have similar, okay, which is the B. Okay, which is the magnetic flux intensity, density. For the electric flux density, we have D epsilon naught E, right? And similarly, okay, in magnetic flux, we also have some sort of relation with our H, okay, but we were using permeability, okay. So of course, with the symbol of naught here, it is actually the free space condition, okay. So the constant is measured in Henry per meter. Okay, your constant is in Henry per meter, and the value is 4 pi times 10 to the power of -7 H per meter. Okay, let me see if we're able to find this value inside. Yes, we can. It is a constant 33. Okay, am I correct? Wait, where is the constant? Sorry, because I didn't long time didn't use this. Okay, if this correct, no. I try again. Constant 17. Oh, okay, never mind. I'm sorry for that. You guys may try. Okay, from this value of mu naught. Okay, should be like this. Okay, constant mu naught. This, but I don't know why it is have the different value. Okay. Oh, okay, because it have 4 pi here. They say we divide by pi, okay, then we have 4. Okay, so it's correct. So you can use constant 33. Okay. Okay, now the magnetic flux through a surface, just like electric flux density. Okay, we will have regions, right? This one we also will be treated having a region. Okay, so magnetic flux through a surface, okay, is given like we have this one over, okay, B ds. Okay, so this is your B and this is your ds. Okay, flux through a closed surface, okay, this one will be equals to 0. Okay, so I will explain later on, okay, why we actually have this kinds like a 0. Okay, so okay, the magnetic flux through a surface is given by this, where the flux is in Weber. Okay, this one will be the unit is Weber, and magnetic flux density is actually in Weber per meter square, or we can also use the unit of Tesla. Okay, so a magnetic flux is a path to which B is tangential at every point. Okay, tangential. So I think you guys may understand. Okay, tangential, if for example, okay, it's tangential. Okay, what is you learn from your mathematics? Tangential is it only passing through one point, right? So this is a tangent. Okay, in electrostatic, the flux passing through a closed surface is the same as the charge enclosed, which is flux dds equals to q. Okay, thus it is possible to have an electric charge as shown in figure 7.22a. Okay, here for the isolated electric charge. Okay, as shown in figure, which also reveal electric flux lines are not necessarily closed. Okay, they are not necessarily closed, but as long as we have like a closed surface, when we have this closed surface, we will treat that flux is actually equals to q. Okay, but we taken from this closed region. Okay, but it doesn't need to be closed path. Okay, unlike electric flux, magnetic flux always closed. Okay, like this, for example, you can see it is always closed. Okay, this is because it's not possible to have isolated magnetic pole. For example, okay, if we divide further, for example, if you have this, right, the main bar, if we divide into two, we will have two corresponding north pole and south pole. If we divide by 4, we'll have corresponding 4 north pole and 4 south pole. Okay, and so on. Okay, now for example, if we desire to have an isolated magnetic pole by dividing a magnetic bar successfully into two, we ended up with pieces having north and south pole. Okay, for example, this one. Okay, it's impossible to separate the north pole from the south, so an isolated magnetic charge does not exist. Isolated does not exist, so this means that we always have flux equals to 0. Okay, flux equals to 0 for B ds. Okay, now we need to see the equation involved with B. Okay, so this equation is referred to as the law of conservation of magnetic flux, or we can call it the Gauss law. Laws of conservation of magnetic flux. Okay, so remember this. Okay, it may be asked in the test or exam. Okay, this definition, right? So Gauss law for magnetostatic field. Okay, so we have a clause. Okay, then we have a DDS. This one, okay, you learned from before. This is for the Gauss law, right? For Gauss law for electrostatic. Okay, okay, so we try to apply the same. Okay, okay, you can see Gauss law for electrostatic, although the magnetic field is not conservative. Okay, magnetic field is not conservative, however magnetic flux is conserved, because we see they will have enclosed flux. Okay, we have closed flux, we don't have open, so that's why it is conserved. For magnetic field, okay, this one is the electrostatic, right? Okay, for the magnetostatic field, okay, this one is may not be conservative. Okay, however, your magnetic flux, okay, you can use the to differentiate, you can use whatever you suit. Maybe you can use M. Okay, magnetic flux, okay, is conserved. Okay, because we have a close. For example, this one, north pole, south pole, we have always closed path. Okay, so by applying divergence theorem, okay, equation 7.247, we obtain, okay, we obtain B ds equals to V B dV equals to 0. Okay, so this one is divergence. Okay, if you can see, if you have a dot products, okay, means this one will be a scalar. Okay, the same for this will result in scalar. So applying divergence theorem, we will have this equation. Okay, B ds equals to the divergence B equals to 0 for volume integral, and this one is for surface integral. Okay, and as you can see just now, okay, B ds is equals to flux, okay, equals to 0. Okay, so or this one we can translate into divergence of B equals to 0. Okay, so we can see here Maxwell equation, okay, for static field. Okay, Maxwell equation for static field, we have let's say this one is for point form. Okay, differential or point form. For this one is divergence of D equals to rho V. Okay, so you can see first you need to see is for static, electric and magnetic field. Okay, so divergence of B equals to 0. Okay, this one is where you get it. This one is from electric, right? Electrostatic. This one is first Maxwell law. Okay, this is divergence of B equals to 0. Okay, and this, okay, I think I shared the link in the previous lecture, actually showing the list of Maxwell law, right? So this one is your first Maxwell law. Okay, first Maxwell law, and this one, this equation is the fourth Maxwell equation to be derived. Okay, this one is fourth equation. Okay, this one I believe you guys learn it. Okay, and this one is from the previous lecture. I share you the link, right? Okay, this one, curl of H. Okay, so this is the first Maxwell equation. This is the fourth. Okay. So the integral form, okay, integral form, we have d dot ds equals to rho v dv, and we have b ds equals to 0. Okay, remarks, okay, this one is with respect to Gauss law. This one is the non-existence of magnetic monopole. This one is conservative nature of electrostatic field. Okay, and this one is the Ampere circuital law. Okay, HDL, JDS, and curl of H. Okay, curl of H, which equals to current density J. Okay, so this is your point form. This is integral form for continuous condition. Okay, this one is only for point. Okay, so similarly, like in the electrostatic, we have related like a potential gradient. Okay, we have a potential voltage. Okay, so we have here potential V to the electric field intensity, so we will have divergence, negative divergence of V. Similarly, we can define also for the magnetostatic field B, we can use divergence B as well. Okay, the magnetic potential could be scalar Vm or vector A. Okay, now to define VA and A involves recalling two important identities. Okay, for example, 3.10 and practice 3.30, you can see later on. Okay, so in the end, okay, we will see that we have the, just as potential gradient for the voltage. Okay, we will define the magnetic scalar potential Vm. Okay, we can have H equals to negative divergence of Vm. Okay, if our J is equals to 0. Okay, so this one is magnetic scalar potential. Okay, this one magnetic scalar potential. Okay, so this one is in ampere. Okay, Vm is your ampere as related to H. Okay, so you guys can read through for the details. Okay, we can see this one first. Okay, we just listed down, summarize. Okay, and then after that, okay, for vector magnetic potential, okay, in Weber per meter. Sorry. So you have the next. We know that we have divergence of B, okay, equals to 0. Okay, to satisfy this equation 7, to satisfy this equation and this equation, okay, you can read from the book for detailed explanations. Okay, at page 321 and before. Okay, 32, you can start from 3 to 318. Okay, so we have B equals to curl of A. Okay, so just as we define V. Okay, so this one, how to solve, you can read from the books. Okay, later on they explain how to derive that, and in the end, okay, we will have, okay, we will have B equals to divergence of A, with A is actually your vector magnetic potential. Okay. This one is in the Weber per meter. Okay, so you have a lot of equation that you can use, but you must remember when to use them and the condition of using them. Okay, this one is Gauss law. So okay. So then you also know similarly, like for electrostatic charge, we have many source of charge for electrostatic. For magnetic, we also have different source of current, right? So we have here as our line current. Okay, you can see A equals to mu naught I dl over 4 pi r. A equals to mu naught K ds over 4 pi r, surface current. And you have A equals to mu naught of J dV over 4 pi r for volume current. Okay, so you can have different source. Okay, so you can see the equation later on. Okay, to help you to see. Okay, so you may see from 755, 756, okay, or 757 the possible equations according to the type of current that you have. But let me just rewrite them again. If you you have lines, because it's line current, right? Mu naught I dl vector and 4 pi r. This one is for line current. A S mu naught K, we have ds 4 pi r. Okay, this one is meant for source current. And then we have A equals to V mu naught of J dV over 4 pi r. Okay, this one is meant for our volume current. Okay, so you can see B is actually the curl of A, right? And you see your A have different conditions. Okay, so if we were to extend this, okay, if we to extend this inside this, okay, sorry, this one we have a vector. If we want to extend this inside this, we will have B, for example, for line current, we will have mu naught over 4 pi L I dl cross R, okay, and R3. Okay, this one is, I think you guys understand already, right? Just like electrostatic charge, we have R3 is actually R2 and the unit vector. Okay, okay, so similarly you guys can try with the source and current, and you will get almost similar question. Okay, so the next important things, okay, you will see in detail from the study books. Okay, from how you're going to get it's explained, okay, how the condition, and then we come across to the last equations, okay, where they actually shown that our magnetic flux, okay, equals to closed loop of line integral. Okay, we have A dot dl. Okay, thus magnetic flux through given area can be found by using either equation 7.46. Okay, they mention here equation 7.46. You can try to see where is the equation 7.46. Have a thorough reading. Okay, so I'm quite fast because I'm worried about my phone's complaints of memory because it's already happening before. Okay, so let's retry on the just a simple exercise. Okay, simple exercise for us to understand the. Okay, now we see the equation. Okay, we see the questions. A current distribution gives rise to the vector magnetic potential A equals to x square y a x xy. Okay, calculate the following. Okay, so whatever is that, we extract the information first. Okay, first they give us current distribution give to vector magnetic potential A, so you get your A. Okay, practice exercise 7.10, and it gives x square y x bar. Sorry, I want to make it clear a bit. Okay, plus y square x y this minus 4 x y z. Okay, so we have W Weber per meter. So the question is that they want us to find what is the B. Okay, the B at negative 1, 2, 5. First question. Okay, so what we have learned, you see B and you see A, right? So what are their relations with this equation? Where you can, so here. Okay, B curl of A, so B equals to curl of A. Am I correct? Yes. Okay, B equals to curl of A. So what have you learned about this divergence? Divergence is actually in the x direction, right? So because this is curl, we only take those that having orthogonal value. If it's not orthogonal, means it will result in 0. Okay, it's not the same as the divergence products, the dot product. Okay, dot product, if it's parallel, it will have a non-zero value, but if it's orthogonal, it will have 0 value. For curl product, if it's orthogonal, it will have non-zero value, and if it's parallel, it will have 0 value. Okay, so here you have x, y, and z. Okay, I just make for your easy reference. Okay, so of course this one is dx, dy, dz. Okay, and a, what a you have? X squared y square, and minus 4xy. Okay, so following the formula that given to you, okay, on this, okay, they gave you the formula how to actually easy to make this. So you will get, okay, you will get that for the x direction, then you have a y direction, then you have a z direction. Am I correct? So for x direction, you close this one. Okay, so I don't need to teach this. This is mathematics. So negative 4xz minus 0. Okay, and for this y, you close this one, right? But however, you can start from here to here. Okay, then you will have a 0 plus 4yz. Okay, then z, you will have y square minus x square. B vector, okay, we have negative 1, 2, and 5. Okay, then we have this resultant value. Okay, so you have to see you okay, you open the brackets. Okay, you open the bracket, then you will find what? Okay, you will close this value, okay, you will insert this value inside. Okay, so you have 4x z x bar x direction, 4yz y direction, plus y2 z square z direction x2 z direction. So what you may do is that you may put the value inside, okay, the x, y, and z. Okay, then you find that you're going to have this answer. Okay, the word important is the working, okay, how you achieve that. And because this is magnetic flux density, so the unit that you should have is WB or meter square. Okay, or what, we have another unit which is Tesla. Okay, so the next, this question is asking the flux through the surface defined by z equals to 1 OX1 85. So it puts the limits. Okay, so it put the limit, and the question is asking about magnetic flux. So where is the magnetic flux? So this one, am I correct? So for B ds. Okay, so the question, okay, you need to define first. Let me see. Okay, where is this location actually? Okay, we have z equals to 1, we have 0, x, this is 1, and this one is and it's mentioned that the range here is 4 and -1. Okay, so you will have surface defined by z equals to 1 here, and x equals to this one. Okay, z x equal to 1, and z equals to 1, so this is z always equals to 1, these parts. Okay, x 0 from this x 0 from 1 until -1. Oh, sorry, this one is a bit difficult to draw. Okay, and -1 to 4. Okay, as long as you know the range. Okay, so then because this is about the surface, okay, you should have what? You should have a double integral. Okay, you should have double integral through the surface divided by z equals to 1. Okay, sorry. So you will have a triple, you have double integral. Okay, and if you can see, okay, if you can see, the limit is z equals to 1 here. Okay, means how I'm going to draw it, maybe like this. Okay, I hope my drawing is good. So this is the direction. Okay, this is the direction normal to the surface, which is in the z direction. Okay, so if it's in the z direction, means we will have dx and dy is our surface, right? So you will have a dx and dy. Am I correct? And of course, your b, okay, your b, because this one is the dot product. Okay, we only need to consider those that having the same direction, those that having the same direction for your b. Okay, so where is your b just now? You take here. For ds is in z direction, right? Okay, initially. So we just need to take those that having the same z direction. Okay, so this one. Okay, so because we know that is similar direction, so we just take it up. Okay, so we will have y square minus x square. Am I correct? Here, okay, because it's z direction. And then we will implement the limits. Okay, y square minus x square dx dy. So for your y is mentioned this from -1 to 4, okay? So you can put your y equals to -1 and y equals to 4. Then your x equals to 0 and x equals to 1. Okay, so this is y square minus x square. So you get your dx dy. Okay, then you will get 20 Weber. Okay, as your example, this one. Okay, because the correct answer is stated here. So it's just solving this, then you will get it. Okay, so with that, we finish with magnetic flux density. Before we go to the week 10 lecture, okay, week 10 lecture. So if you guys notice, I provide the lecture video of the supplementary material for this curl of vector and Stokes theorem. Okay, for the supplementary material. So you guys may refer to that. Okay, to actually know about this curl of vector and Stokes theorem. I believe the lecture explained very extensive and very elaborative. Okay, so hopefully, but if you have any problem, you get me may contact me. Okay, so with that, assalamualaikum warahmatullahi wabarakatuh, and good day everyone.